OK, alors, bon après-midi et puis bienvenue. Très heureux de vous accueillir encore une fois pour un autre séminaire quantique d'Ivado. I'll switch to English. So it's with really great pleasure that I'm introducing my friend Matthias Christandl. Matthias did, so a few words, I will be brief because I would rather listen to him, but he did his PhD in Cambridge with Arthur, under the supervision of Arthur Eckert. And then he has had the faculty position first in Munich, then at ETH in Zurich, after which he moved to Copenhagen, where he is now full professor in the Department of Mathematics. He's done outstanding work. He's really one of the leaders of his generation in quantum information and computation. He's done seminal results in various areas, starting with work that I've used on quantum perfect state transfer, but more specifically work on tensor networks with application in algebraic complexity and so on. Many results. He's also really a builder. He's been one of the leader of the Willem Center called QMath in Copenhagen. And he's also founded the Novo Nordisk Foundation Center for Quantum for Life. He's very active. He's been chair of the conference series called QIP or QIP for Quantum Information Processing. And he's received many prizes and decorations, and he's in particular a member of the Royal Academy of Science in Denmark. So it's a pleasure to have you, Matthias. The floor is yours.
Well, thanks, Luc. Thanks for this for the kind words, and it's a pleasure to be here and be back in Montreal. Meeting also in addition to Luc, also Louis and Fred and other researchers in quantum information theory. With of course Gilles Poisson and Claude Repot. It's one of the birthplaces of the field. I'll report on a project today that somehow combines tools for machine learning with the idea of quantum computing, and it's a project that was very interdisciplinary, and I'll say more about this. It's about how to use quantum computers for biology, for biomolecular free energy. So it's really spanning a broad area. So I'm certainly not an expert on this entire project. I was just kind of like coordinating and leading the project, and I hope you bear with me that maybe I'm not the expert on every particular thing, but nevertheless I was very excited about this project, and it took a lot of I put a lot of my energy into it, and yeah. So if you want to read more about it, you can find it here on the archive, or maybe approach me afterwards. Right. So, and if you have any questions, just interrupt me and just ask. Actually, I don't have that many slides. So, how much time do I have actually? What's your usual? 50 minutes. Okay, yeah. Okay, good. And Luc told me before that some of this was actually inspired by a seminar we started. Seminar series we have in Copenhagen where people, where there's free sandwiches and free food while speaking. But I have to say it's much more polite here because I had my food before. Like in Copenhagen, the speaker is supposed to eat afterwards. So, anyway, so here we go. So this was actually a project led by 7 people. So I was coordinating these 7 people, and it's spanning really from biology, so from drug discovery. We have a partner here, Jesper Falkenhoff-Borg, to biology with Christandl Larsen. Then we have Anders Krogh, a machine learning in biology expert. And then coming to quantum chemistry, quantum chemistry, and then down to quantum algorithms with Aram Harrow from MIT and myself. So really spanning this whole broad broad thing in order to make this possible. We're being funded by Novo Nordisk Foundation, and maybe Novo Nordisk probably maybe have heard of it. Novo Nordisk has at the moment is very much in the news due to this weight loss medication Wegovy and Ozempic that they have on the market. Um, we're also funded by the Wellcome Trust or the Wellcome Leap, a subsidiary of Wellcome Trust that has funded part of this research and initiated it. Part of the work has been done on Gefion, which is one of the largest NVIDIA computers. I think it's like number 20 in the world in Copenhagen. That's a new machine. So we've also been running something here. And Luc alluded to with a grant from the Novo Nordisk Foundation, I founded this Quantum for Life Center. Maybe you can see sort of like what are the associations you see with this? You see like the wave particle duality of quantum mechanics, and then it's also kind of like maybe air bubbles and some grass and like wind going through, doing some waves there. All right, and then there's also NQCP, which is also a large program from the Novo Nordisk Foundation in Denmark. All right, so these were the group leaders, but the real work has been done by this entire team. So there's a bunch of people in each of these groups, and Lisbeth, the coordinator for this. This was very exciting. It was very intense, and because we were working in a very sharp timeline, and so there was a lot of Zoom calls. It was a team flying over back and forth. So it was an intense project. Anyway, so it was new for me. Usually I've been working in collaborations with 2 or 3 people, and now it's like, I don't know, 25. Okay, here's what we wanted to do. We wanted to understand how to use quantum computers. So people say quantum computing will have impact and one of the things that quantum computing might have impact in is drug discovery, life sciences. And there's a specific reason for this. And the specific reason for this is that quantum computing, that molecules are built out of atoms, and atoms are quantum mechanical objects. And when they interact, there's a difficult to describe quantum mechanical interaction. So there's the idea, and this is Richard Feynman's idea, to build a machine out of controllable quantum systems, such that with the interactions in this controllable fashion that you can control like a computer, like a quantum computer, that you can mimic, you can model, you can compute what this other quantum system is doing. So this sets life sciences and biology apart from any other application you might have for quantum quantum computing for something, right? It sets it apart in that sense that there is actually a quantum computer to be able to simulate a quantum system, and we have relatively good understanding why quantum computer is being being good at this, right? So like very intuitive. Quantum simulates quantum, and so I can say more about it later, but I want to first give you an overview of this project. So the project is about trying to understand now whether a drug molecule targets to a biological system like a protein, like a large molecular structure, how they target, or whether or not the drug will target or not. And traditionally you would now say like, okay, if it binds, then the energy is lower, and if it doesn't bind, if there is a binding, if the binding energy is somewhat negative, right? So then they will bind. And things are a little bit more difficult in these large biological systems because there's like water around it, it's at ambient temperature. These molecules move, and so it's not actually the energy that's the right thing to do. It's actually thermodynamic quantities other than the energy you have to compute, namely the free energy. And I'll say more about the definition of free energy, but this is it's a thermodynamic quantity. Maybe show of hands, who's heard of the free energy? Just to kind of like, okay, very good, excellent. So, well, perfect. So so we want to compute this object, and then there is this molecule. It's like a protein. It's like huge, and the drug molecules may be a small molecule, but in order to figure out, whether they target, you can't just take the molecules, these molecules, and just like kind of like load them on a quantum computer. And there's a completely silly reason for why this will not be possible in the next decades. It's because quantum computers are not expected to be so large. They will be expected maybe to have like maybe tens, hundreds, maybe thousands, maybe even maybe thousands of reasonable of high quality quantum bits. But these molecules might be much larger. Okay, so you have kind of like no chance of putting the whole thing onto this quantum computer. But as my colleague, actually Markus Reyer, always emphasizes, it would also be stupid to try it. So it's also like not necessary to do it. And the reason for that is that most of this molecule is kind of like hanging out there in the background and it's kind of like flopping around. It's kind of classical. And so you don't want to do that. So there is the project starts with this question and then says like, hey, we have to only model the region where there's really some quantum interaction going on between the drug molecule and the protein. And so you have to, that's the QM region. Then you take that QM region and you put that on a quantum computer. Okay, this is what you want to model on a quantum computer. And you do that here. And then you have to take into account that things change when all this molecule wiggles around. And that is somehow where you have to do now many of these configurations. You have to understand how they flip-flop around. And that is what gives you the free energy part of this. And then hopefully at the end, you kind of like have something that says like, hey, it's, it binds, this one doesn't bind, etc. So you can do some kind of ranking. Okay, so we want to provide a tool in some sense to do this. We want to understand how to compute this. Maybe a couple of words more about like this entropy versus energy versus entropy. So when systems are sort of like weakly, and we start by first looking at this x-axis. So you have systems that are inherently sort of like less correlated, and systems that are stronger correlated, and for systems that are less correlated, for instance, like a water molecule, or you have systems that are very strongly correlated, systems that maybe contain metal atoms that really have a lot of electrons that like to bound in some like complicated fashion. But really the problem is not that something wiggles around. Where the problem is like, okay, it's like a static problem as I explained before. So it's really static. You have this and this. Do they bind or not? Then it's like you have to compute the energy. When things move around, then maybe you can also have weak quantum correlations. Maybe just some proteins interacting, or you can have like stronger quantum correlations where the correlations themselves are sort of like intertwined with the wobbling around of this molecule. So also there it's sort of like a grading of like smaller correlation, but higher entropic complexity, so more flopping around. So and this gives you sort of like this landscape in some sense. And with the quantum computer, we would like to kind of like attack, now this project and down here, people have studied, and we wanted to with the project to attack this top part. So the top part, we're having to do these correlations go hand in hand with high entropic complexity. And why would we do that? Well, because most of the biological systems will be the relevant question to ask. And so if now people come and say like, hey, what we want to do is quantum computing impact in biology, or we want to show that we can quantum computers, people will make very bold statements like quantum computers will revolutionize drug discovery, right? Well, I mean, let's see, right? I mean, we have to figure it out. We have to understand if we want to do that, how we would also do that. Maybe one more word. It was nice so many people showed hands. There's, of course, also different types of free energies, and it's a bit of a complicated zoo there. I don't want to go too much into detail, but I wanted to just show you a graph. I wanted to flash some kind of formula for the for the free energy here. And I wanted to kind of mention that you see, you can still think of it in the same way as you think of it like you have the free energy, like you would think about the energy, and they have an unbound state, and then you have maybe a bound state, and you want to understand maybe the path from the bound state, from the unbound state to the bound state. You know, do I actually have a delta? Is the bound state, does it have a higher free energy or a lower free energy, or you know, how high is the barrier? So you would like to compute free energies, maybe free energy differences, paths through free energy landscape, etc. And a free energy by themselves is um, is something where you have to sample, where you have a Boltzmann factor, so where you go through configuration space, right? Go through configuration space, and configuration space now here means that we're working in like the Born-Oppenheimer approximation. When we think about a molecule, we think about a molecule as we fix the nuclei somewhere in space, and then we say how high is the energy, and we look how high is the energy of the electronic energy for that system. Okay, and then you modify the positions of the nuclei, and you see how, and you obtain an energy landscape. And here is sort of like a drawing of this energy landscape. Yeah, that's the setup. And of course, it's not a two-dimensional energy landscape, but a multi-dimensional energy landscape. And you, in principle, you would want to now integrate or you know the partition function, compute the partition function, which is the inner part here, or compute then the free energy coming from that. You want to compute that, and you see the problem you're having is that there is a vast landscape you have to sample across, and you have to kind of integrate over, and you want to and this is just infeasible. So you need to understand what to do in order to attack this problem. How can I evaluate this free energy? And one important point here is that if you look in the formula and you look at the energy formula, then there is the so basically the you can think that for every positions of the nuclei, the system is actually in the ground state. So there is actually no electronic excitations in the system, because the electronic excitations, they have a much higher energy. So it's really like the so you for a given configuration, you really have a ground state energy problem to deal with from a quantum, for the quantum experts now, from a quantum mechanical point of view. So and what you see here is that the energy somehow enters this formula in an exponential way. Yeah. So if you get the energy wrong, like the energy for configuration, it actually ends. So it's important that you get this energy right here, because it enters the formula in an exponential way. Yeah. Right. All right. So let's see how we approach it and how we would do it. And maybe actually before I continue, let me understand your background. So I know there's some, yeah. So who's a computer scientist? Who's you can also double count if you want. Who's a physicist? Okay, who's a mathematician? Um, you're a minority here. What else do we have? Engineers. Oh, we have engineers here. Very good. Okay, excellent. And yeah, good. Cryptographers, Louis. Yeah, okay. There are also two cryptographers. Very good. Excellent. So, right. So what are the challenges? And I already told you a little bit. One of the challenges is that you have way too many of these configurations to compute. Okay, infeasible, basically. Then the molecules are too large to be represented on a quantum computer. Okay, so how we solve these two problems? So the too many energies you solve with machine learning. So essentially, you start with this classical model that is typically called molecular mechanics modeling, where it's basically a, you know, you imagine like that the nuclei are connected with springs, with different strength springs, and you have some model for how these springs, like the strength of them, and you solve that, and then you that's your first model, and then you try to improve on that. And how do you improve on that? You improve on that by machine learning modeling. So use machine learning to improve over this model, by taking in more and more quantum computed data. I will tell you more details about this. And the second thing is that an individual data point of energy will be too expensive, and that I already mentioned. Also, that we have to kind of like reduce to the smaller quantum core within this larger system. And so here's basically our pipeline. So like you had to get used to this term. It's a software package if you want it. And this we call it FreeQuantum for obvious reasons. And it's really a large software package. So it takes in a structure. Okay, so a structure means like you take in a molecule. You say, here's my protein, here's my drug molecule, and then it does the first you do stuff without first you do the thing without you compute this free energy. Maybe I say also more. It says free energy perturbation. Say more about it later. You compute this free energy by just starting somewhere from a configuration and then somehow solving, as I said before, Newton's equations. So you time evolve, right? You time evolve the system, and by some sort of like a godicity theorem in the background, you move through the system and sample thereby in an appropriate way the phase space, and thereby obtain sort of like the first value for this free energy, the first guesstimate, right? The first guess for the free energy. You get that, but just by this spring modeling. Okay. Then you're like, okay, well, maybe there's these quantum effects. Maybe they're close to this molecule, and we chose like a metal in the middle. So what maybe we should look at this path, and we should try to understand the region where the quantum interactions go on in more detail. So you select from this path, right, through phase space. You select some pictures, like snapshots, okay, of where the nuclei are, right? The nuclei positions here, then you time evolve nuclei positions here, and so on. So you take these snapshots and you say like, hey, for those snapshots, let me now look at this quantum region. Okay, let me look at where these correlations are strong. And then let me in this quantum region, let me use a relatively cheap quantum model to solve it. And in our case, this is DFT. So density functional theorem theory is a relatively tractable method. And then for these snapshots, you create training data. Okay, and this is called a QMMM. So you create some training data, and then you try to upgrade. You basically upgrade your previous model. You train it on this way around. Yeah, you train it a new machine learning force field, so a new force field, so a new kind of like new forces based on that, right? And then you're like, okay, well, that gives me the output here, the second output. Okay, that's called MM plus ML1, so machine learning 1. So this gives you the first correction to the system. But then DFT, it has uncontrolled errors, and it's also like you want to kind of like be more precise than that. If you have a very strong quantum correlation where it's not going to perform well. So From that, you select even a smaller region where the correlations is stronger, and you're saying like, hey, now I'm going to use a more expensive method. And this more expensive method can be a very advanced quantum chemical method, or in the hopefully near future, a quantum computer. Oh, here is where you slot the quantum computer in, and then you're going to compute here, but you again have fewer points. Okay, so then and then you train on top of the previous model. Okay, and in order to get this free energy perturbation, a better one, a corrected one out. So this is kind of what we built. This is the software, and it's ready. So when the quantum computer, we also estimate like which sizes of quantum computers will be relevant. It's ready, it's there. So if the quantum computer comes, you can slot it in here. But it's exactly in there that it will be needed in order to obtain this quantum advantage that people promise. So without this scaffolding around it, a quantum computer will actually not be able to deliver quantum advantage for this problem. Yeah, any questions at this point? Okay, so in some sense, it's a software product. Yes. Yeah, this is a they have software tools to do that. Of course, they also have a chemical intuition of where where the interaction is stronger, and you will see that later. We, for instance, have a ruthenium. Ruthenium is a metal, and it's a ruthenium-based cancer drug that we kind of like looked at. And this ruthenium, yeah, people know there's some experience that the certain methods don't work well and certain other methods work well. But there's also another thing, and you see it here. It says like you have some yeah. So in your training, then you have some uncertainty quantification also, but generally you would but generally you know where the methods work better and where they work worse. And also they have some software tools available for that. But again, I'm also not a chemist. So I'll have to refer to my co-authors. Yes. Say again. I can repeat the question. You said like you make data from lots of computation. Yes. And then you train a machine learning model of that data. Or is that? No, no, you create better data here, right? And you train it to improve it, and then you improve it further.
But if you don't know yet, like in that state, you don't yet know what the best data is because you haven't used the best possible methods. How does the machine learning algorithm know what direction to improve the data with? Like, what's the training set to make it better?
Oh, you're declaring like you're declaring a region. So you're declaring a region where you want to improve, where you know from some other software tools, or you have already declared that that you want to improve the quality here. So you have like kind of like some embedding method. You declared where you want to do it, like in a specific region, right? And then you use that to improve. Did that kind of like answer?
Yeah, I think that kind of makes sense. Yeah.
Okay.
Thanks.
Yes.
Hello. So the initial guess you did using some Monte Carlo simulation, right?
No, it's so the initial is what they call molecular mechanics. It's molecular mechanics simulation.
But you're randomly sampling from some.
Actually, they kind of like walk this path through. Yeah.
Yeah. So
Yeah.
so is it clear that these sort of like Markov chain based methods, like why is the machine learning necessary at all? Why not just do this usual Markov chain Monte Carlo kind of thing? Will not that not work as well?
No, the machine learning here is being used to improve on those models. Okay, so you have kind of like a background force field, and then you want to improve that. Right. So and yeah, but again, I'm not an expert in how this works, but here this is an active learning loop, and down here there's like a transfer learning loop. But I would also have to look up now details. Yes. Okay, more questions. There's one more.
Get two quick questions. The first one, if you zoom out a lot, right? Because you're saying here, if you look at it on the drug design industrial workflow, it's massive, and there's only tiny part that involves quantum mechanics, and now you're suggesting to replace the conventional classical methods with this workflow that
Yes.
eventually will have a quantum computer. From like a workflow wide perspective, are there some estimate as to how much the improvement given by the quantum computer will impact the accuracy of the full workflow?
Yes, I think this is to a large degree an open question. I mean, because it's very hard to propagate the error estimates. So for how to propagate error estimates through this machine learning to the other side. So I guess my colleagues mostly that have dealt with this machine learning here, they have made sure that these learning loops here converge, and that thereby they have a good confidence for them, like kind of like yeah, homing in at the right place. But it's of course not. And they have also adjusted the size of these regions according to whether or not it improves or doesn't improve anymore, right? So you can kind of like imagine that you take this core here, you start, you say like, oh, I take a small one. Let's see what happens when I make it a little bigger. And then if it stabilizes, then you're kind of, okay, that was good enough, right? And but rigorous error bounds are difficult to obtain. So here we have rigorous error bounds for our algorithms, of course, if we want to run in the future. But then how do they propagate through? One way is to validate, of course, the accuracy of this is to compare to experimental data, because there is sometimes experimental data available. And so that's one way of doing it.
Nice. And my second quick question is, you mentioned estimates as to the size of the quantum computers that you would need.
Yes.
Can you share more about those?
Yeah, we can say more about it later. All right. Yeah, I wanted to say a couple of words. Instead of free energy here, we're using the word free energy perturbation, and this is a specific technique to compute the relevant free energies. I just wrote down the partition function. Really, we're not interested in absolute free energies, or we're not computing them. We're actually looking at binding free energies. So basically, you want to know is the bound one minus the what's the difference between bound and unbound? Okay, so that was like the delta A. Is this positive or negative, and what magnitude does it have? Now, this is actually a difficult problem if you write it like this, because maybe it's all just intuitive now, right? But the bound and unbound case, the configurations you would have to sample over are very, very different, right? In one case, like they're out here, the target molecule, the protein molecule is here, and in the other case, they're like close together. Okay, so they're actually very different. So if you start like some sampling algorithm and you can't sample properly, through everything that you want to sample through, then you will have errors that don't cancel. Okay, so you would like to have more error cancellation in this process. So you would like to sample over very similar distributions. And so there's a trick, I would call it a trick, that you take this difference and you make a telescoping sum out of it. Okay, so you imagine that they're unbound, they have a large distance, and bound, they're close together. And you could now say like, okay, so let me just look at the situation, how it comes in at these different places, and then always like just sample the difference here. Okay? And this apparently is already pretty good. So you can do that better. And so it's one of the techniques to do this. There's another aspect, and I have actually comes with a picture, because I was working with real biologists, so they actually they didn't buy this sort of like more physicist thing of like let's look at this model system, right? And physicists, like I'm coming from that direction. It's like, okay, let's look at the model system, right? I mean, Luke would even take it to be integrable, but you look at this model system, and but they wouldn't allow this. Okay, so like no collaboration with model systems. Okay, so if you want to collaborate with them, you got to have real stuff. Real stuff apparently has water around it. So you want to kind of know if this protein here bounds with this target here, but there's all these water molecules around it. Okay, so and they're moving also around. So you want to compare this situation to this situation, and you don't really want to talk about all these water molecules the whole time. So what they do is alchemical, right? So they call it alchemical. Maybe they do something non-chemical, right? I mean, that's what alchemical stands for. So alchemy, right? So yeah, okay, alchemy is. So they're doing alchemy. So they're very proud of this. It's surprising, but so they're basically having the protein and ligand interact, protein and ligand, right? So protein and drug molecule, and then they're kind of like imagine right here, right? Here's protein. So protein and the ligand is here. This is a drug molecule, a mock-up. And then they're like, hey, let me switch off the interaction. So now I kind of like encapsulated it. Okay, this is like this is of course not physical. Okay, it's just like, oh, they're close together, but they're not interacting anymore. But mathematically, it's doable. I can just like throw out terms out of the Hamiltonian or the interaction terms. Okay, so instead of like computing the difference of this situation and this situation where they don't have control of these water molecules, they like take this situation, then they switch off. Now forget the directions of these arrows. They switch off this this interaction, so they kind of like encapsulate this. They compute that difference, and then this here actually, then they compute the difference from this one to this one. You see, then basically only like some water molecules moved a little bit, but the interaction here was not the problem. And then again, when you are here, you switch on the interaction. Okay, so somehow they call this also thermodynamical cycle or alchemical. I don't know. Yeah, and then you get a nice formula. So you can basically, I'm not going to go through this formula now, okay? But that's the idea, okay? You switch on and off these interaction, and this way you move forward, and then you have a lot of different ones you have to compute, and those you do again with this technique up here. So this was in a nutshell, right? In practice, people will use software packages for this, okay? So, but as a background, okay. Good. I can ask for questions, but I'm not sure if I can answer them. Very good. Yeah, here comes machine learning. Like I'm even less an expert there. So, yeah. So the machine learning potentials, they're typically trained on the energies and the forces. So the forces, of course, a derivative of the energy, but for us, we actually use each computation of an energy is hugely expensive, and we're going to come to that either on a quantum computer or on a normal computer. So therefore, it's good if we only can deal with energies. And here is some data that should convince you that things converged with a number of like loops in this. It looks kind of nice, I think. Okay. Anyway, and then use transfer learning to yeah, I guess you know more about these learning methods. Good. I want to tell you, I think this is the sort of like exciting part of the part where kind of like my field comes in, the quantum computing part, right? The quantum computing part comes in here in this core, and you start with this big region, okay? So with this big molecule, then you go to this first quantum mechanical region, and then you look into even smaller fragments. Maybe you just look at one of them, but you could also look at several of them. And therefore, it's called a QM-QM-MM embedding. Okay, so for molecular mechanics, also known as classical for us. And then QM is this DFT is the first QM, and the second QM, that's sort of like more expensive method. Let's talk about what it would be. Okay, so quantum region is quantum electronic plus interaction. And so you see, right? So at each level, you then have like an effective Hamiltonian for your system. So if you think of this quantum region here, it's the effective, the electronic Hamiltonian of this quantum region plus an interaction that comes from the outside. And here, if you look to the quantum core, you get the Hamiltonian for the electronic region in the core, plus, and then something from the interaction from here, what you dealt with DFT. Okay, so there's like a double embedding in order to get it down. And I think this is one of the innovations of this project. So now I wrote traditional quantum engine. With traditional, I just mean like a normal computer quantum chemistry. Okay, not quantum computer chemistry. Right. So let's do a little bit of that, because I think that's somehow was exciting. So how many of you have had, I mean, quantum mechanics? Okay, how many didn't have any quantum mechanics? Okay, very good. So how many of you have seen fermions? Okay, well, it's all a lot of people. Very good. So, so the full problem is, right, the full problem of like computing the energy for a molecular system, is the wave function depends on like nuclear positions, right, and which they call capital R, depends on the time, and depends on of the of the electrons. Then, of course, what we do is we look at like stationary states. So we look at the eigenstates of the system, and with you know, once we have understood what the eigenstates of the system are, the time-independent one, we can solve the time-dependent one with our known rules. And then we do the Born-Oppenheimer approximation, and the Born-Oppenheimer approximation says that, hey, this wave function, really nuclei are a factor of 1,000 heavier than the electrons, so we're going to treat them as classical. And for each configuration of the nuclei, we're looking at the electronic energy. Right? I've mentioned things before, but I wanted to kind of like put formulas to it now. Then something interesting happens, because now you really want to now solve this electronic Hamiltonian, right? You want to solve the eigenstates from the electronic Hamiltonian. And and even to get to that electronic Hamiltonian, you would have to do a few steps, because the electrons, right, when they go around the nucleus, they actually have an infinite number of possible wave functions to sit in, even in right. So if you solve the hydrogen atom, right? You solve the hydrogen atom, then you have an infinite dimensional Hilbert space, right? Because the L2 of R3 is infinite dimensional, and then if you have if you just have molecules, then, or like larger atoms, things get more complicated than that, right? So in order to solve it numerically, the first thing is you have to choose where to cut off this infinite dimensional Hilbert space, right? Because the computer is only finite. And this is an art in itself, okay? I mean, chemists have like worked on this for decades, and they're extremely good at this, right? So which orbitals, right, to choose and how to craft them for a given problem at hand. And yeah, so but let's assume now the chemists come and like say this is really good set of orbitals to choose. This stuff you can neglect, etc. And those we call maybe the one particle wave functions. Okay, so and in each of them you can then start to put in, and the number of orbitals that you want to keep roughly scales like the number of electrons you have. And you can kind of like the number of electrons is also roughly like proportional to the number of atoms in the system, right? So just imagine you have like, right? You have a number of atoms in the system, number of electrons will scale, and it's kind of clear that if you were to, if at each atom the electron just has a few positions to place itself, right? So like maybe position 1, like it can be in this wave function or in that one, right? Then I would have for n atoms, I would have, I would have, 2 options here and 2 options here, etc. So in total, actually, it's an exponential number of options. It's an exponential number of options for the electron to sit. And this is sometimes known as the curse of dimensionality. And that simply the number of configurations is very large, and not only do you have many possible positions, but also the electrons can be in superpositions of them. Right, so they can be like in a linear combination of all of them, and so you want to solve that. So this is and we would call it, like physicists would call this, okay, I'm doing an exact diagonalization, and in chemistry, people have a very funny term for this. I find it extremely funny. They call it full CI. Okay, it's like I'm doing the full thing, right? So they're basically doing the full thing they call full CI, and the thing that Hartree, famous earlier in the 20th century, he basically said, hey, let's just forget completely about these superpositions. Let's just look at orbitals of like putting an electron, like let's just choose an orbital basis for this one. Let's put an electron there. Let's choose let's choose the orbitals, and then let's put electrons there. And this is the Hartree-Fock method. And if you look at it, and then the wave function here is also known as the Slater determinant. And optimizing over this is sort of like, there you got rid of you only have to choose these. So you get rid of this superposition, of this exponential superposition. And so somehow if you want to do this in practical chemistry, you sort of like, you start thinking about this case. Okay? You start thinking about this case, and then you're saying like, hey, if that is one configuration, like how I put the electrons there, let's improve on that. And when you improve on that, let's take these configurations and let's swap out one of the positions, okay? Or let's swap out at 2 positions. So, and then if you call this one configuration, and you now swap out one, you allow like a variation on one of them, and you allow superpositions, then it's kind of like these configurations, they interact. Okay, they're not interacting. Okay, they're not interacting. It's a misnomer in some sense, but like they're somehow, I'm allowed to take superpositions over them, and therefore it's called a configuration interaction, like CI. Okay, and the S stands for singles. Okay, to replace the singles, and now you can do like, okay, I'm going to do this, like I replace 2 of them. Okay, that's CISD, like configuration interaction singles doubles, and then you can go all the way up, and when you have them all interacting, that you call full CI. So that's where these names come from, because they're kind of like bottom up you know, this is really solving the problem, and these are all approximations. Okay, and the important thing to remember is that this original problem here is actually exponential in size, and you don't want to do that. So, very good. Yeah, any questions? Exponential explosion. Here. Okay. So yeah. So down here you have so maybe important for us also is that up here, right? When you solve it exactly, you would get approximation guarantees. Like how good is it? Down here you get fewer configuration guarantees, and the more you go up, the more computational challenging you get. And up here you can actually do like other tricks to solve the full problem. And it's one called DMRG or tensor network methods. It's actually not so unfamiliar with the machine learning, some of the machine learning literature, as a proxy for the full CI. You can also kind of like do an approximation to full CI, which in practice works very well. Okay, any questions? Okay. Yeah, here are the biological systems. So we use two systems. One is a model complex. Okay, so it's like I have no idea. But it's used for testing purposes. There's in particular also experimental data available. And this here is our ruthenium complex. So this is like a ruthenium system. It's very complicated, very highly correlated system. And this is your protein. Okay. And yeah, so the electronic structure is challenging. So they really look like this big. And we did full computational runs on it. I mean, not on a quantum computer, of course, but with these chemical methods as a traditional engine in the middle. Yeah, okay, so there's a bunch of papers that my colleagues wrote on how to do this, on how to build this entire machine. And then here is some data, okay? So you can do now, this is just a classical, this is like the first loop, okay? You get some number, then you do so this was like top left in my pipeline, then you go over to the right. This PBE is a DFT type method, so it's a single embedding, and then it changes. But you see, the interesting thing is that all of these numbers, they're still kind of like in a similar ballpark, and they are coinciding with experiment. This is quite remarkable. I mean, if you think about how absurdly big this problem is and how complicated this pipeline is, this could easily go off by a factor of 10 in one direction, or even that. I mean, apparently it's even like already great that the sign is correct, right? It's like binding, right? The sign is correct, it's negative, right? So we're proud of that. And here you have like a different, I mean, this is a huge software stack with like 25 people involved, like programming this stuff. And then here you have this QMMM embedding in different variations and different strength. So this is like I don't know what this is. Coupled cluster, single double. So coupled cluster. I don't know what L is. Unitary coupled cluster. I don't know. Coupled cluster, single double, triple. Maybe only some of the triples. Okay, and but you see, it kind of like matches the experiment very well. So very good, well done. And the interesting thing is, of course, that you can apply it in cases where the experiment is there, and you can also apply it in cases where it's not there. So you can basically run it on this other complex where you don't have reference data, and then you can also see that now you see already that there's like a bigger variation, and the different methods bring in different correlations and so on. But the chemists that have been running this are very careful in making sure that these runs are consistent and that things are properly converged. So that there's some meaning to these error bars. Yeah, so I think what is good to see is that the method works, and it is the implementation seems to be correct and converging, and that was really many months worth of effort. But at the core of it, you then have still these uncontrolled errors. So what you can do is, right, you can now try to slot in the quantum computer. And so in the future, we want to do that. What are the advantages? Why would we want to do that? First of all, you get accuracy guarantees. Oh, in terms of my biomolecular simulation quadrangle, if you remember this square, also known as square before, I was kind of like, the problem we tackled here was on the top left. Okay, so it had this configurational complication. Okay, it had the sampling, but the correlation wasn't so strong as that these traditional chemical methods would fail. Okay, so they're challenging. It's challenging for them, but it's possible to carry it out. Okay, when you now put in a quantum computer, you can then move to the right, more towards the right. Okay, so you can go for more correlated systems, and on top you get accuracy guarantees. Of course, the problem with the accuracy guarantees I mentioned before is still that when you then use it only as training data, generating training data for the machine learning loop, then of course you're losing some of these accuracy guarantees. But at least on the energy production level, you get accuracy guarantees. Ah, yeah, here it is actually. Okay, so we built a computational framework that allows to slot in a quantum computer. Okay, you bring a quantum computer, so we can immediately use it. I think it's ready for quantum advantage when the hardware is. And we thought about how big a quantum computer has to be for this to be actually impactful here. Okay, there's of course a lot of people that say, hey Matthias, why didn't you use the current quantum computer for this? And it's like, well, the current quantum computers, they're there, like they exist, but they're very small and they're very noisy. And that's all fine if you want to use it for a model system, but not if you want to use it for a ruthenium-based cancer drug. Okay, then you can't go and come with the current machine. So it's sort of like squaring the circle. So you can either do it for a model system and then for a small machine, or you really want to estimate how good it is. So so we propose to actually do the energy computations precisely. So there's also heuristic methods and people proposing heuristic algorithms for doing energy estimation. One is called variational quantum eigensolver, VQE, and other things. We're more on the sides like, hey, if we're going to do this, we want to actually harness the fact that the quantum computer will actually be correct. Okay, so let's do that. So we looked, and then what you really want to do is one type of algorithm called quantum phase estimation. Who's heard of quantum phase estimation? Okay, very good. Who's not heard of quantum phase estimation? Okay, very good. So quantum phase estimation is basically an algorithm that lets you estimate the energy, right? The energy. So if you manage to prepare your system in a ground state, okay, and you just happen to not know what the energy is, then quantum phase estimation is an algorithm, a quantum algorithm, that will be able to give you return you the energy in a very efficient way. Okay, and this is sort of like, you can think of this as like a family of algorithms, even more like a blueprint for an algorithm on which there are many then variations and improvements and so on. But what happens in this quantum phase estimation algorithm as an integral part is you have to do time evolution with respect to a quantum Hamiltonian. Okay, so you got a quantum system, and starts in some starting state, and you need to time evolve it. Okay, and the main cost of this algorithm actually is because the time evolution is very expensive. So, and it's especially challenging in chemistry because it's not like you got a structured Hamiltonian. It's basically some random matrix that you're gonna get. I mean, it's not random in that sense, but like the chemist will give it to you after they've done like a double embedding and God knows what, and chosen some orbitals. So to you, if you see it, it looks roughly like some kind of like random matrix with random entries in. So the fact that it's so unstructured will actually lead to many terms and to very deep and complicated quantum algorithms for this. So we looked at this and wanted to see if we can improve them. And there's two aspects to improvement. One is you can say like, hey, how many quantum bits do I need to run it? And the second is like, how deep is my circuit? Like how long does it take to run it? Okay, and in quantum computing, we're being challenged at both sides. First of all, we don't have many qubits available, and if we're going to have better, and they're noisy, and so if we have better qubits available in the future, we want them to be better, but we still try to minimize the number. So, and here you can sort of see that basically this is like how slow it is. Okay, so on the y-axis, and this is how many qubits you need, how many logical qubits you need. So and this is actually for benchmark. This is not for the particular one here. I maybe have some other graphs later. But so one is we use like a so-called single ancilla phase estimation. So it's kind of interesting. You only need to the amount of space you need in your quantum computer, the amount of quantum bits, is actually just only the amount that you need to model your other quantum system. So you actually have no overhead there. So if you want to model like a system with 20 fermions, 20 fermionic modes, then actually a 40 qubit system is fine. This is like it's optimal. So so that's very good. Or 40, 41, right? So this is good. So we worked on this framework, and then we try to optimize. And one thing we noticed was that in these chemistry Hamiltonians, some of the terms are very large and some of the terms are very small. And there's two algorithms. One algorithmic framework called QDrift, which is really good for like small terms, and another algorithmic framework that's really good for large terms. It's called Trotter. Yeah, there's a Trotter reminder here, but never mind. And so we interpolated between the two. Okay, so we actually built a framework so you can put yourself in the middle, so that can deal in a good way with both. Harness some of the yeah, and so you see that like in this work we did improve substantially what was there before, and these methods here, they are the total runtime is maybe higher, it's maybe lower of them, but the problem is that they need substantially many more quantum bits to do. I'm out of time, but I'm also done. So that's very good. I want to tell you one more thing, which was fun. So then, but usually I mentioned that you need to, that quantum phase estimation works well if you have already an eigenstate or a ground state prepared. And that's not the case usually. So you want to find out that it's easy to prepare such a ground state has good overlap. So we ran a project on this for such embedding methods, and we found that in the typical instances we find good overlap. So that's good. So it's all good signs, and then we wanted to get a really good estimate, and we used this Gephion computer that I mentioned before. And one of my postdocs, he programmed for 2 years, like the fastest simulator for that exists for simulating quantum circuits, specifically time evolution. So if you want to know more about this, talk to Marek or me. It's called Phase 2. All right. Thanks for the attention. I think we developed here, maybe conclusion, we developed a complete modular autonomous computational pipeline. Sounds like an advertising. It's compatible with traditional chemistry and with the future fault-tolerant quantum computer. And yeah, it adapts to your computational resource. Maybe I only mentioned it once briefly. And the modules can be exchanged and upgraded. And we ran it actually on a big system. And yeah, I think I hope it opens the path to quantum advantage for biological systems. But of course, the remaining path is long. So thanks for your attention.
Very much. We already had a few questions, but along the way, but are there others? I have one. When you had your test molecule, right? And the computation without the quantum computers were rather good.
Yes.
So am I understanding correctly that this is a case where going through a quantum computation is not where you generate advantage. Is that correct?
Yes, in some sense that's right. I mean, what we still would hope to get, I mean, it was to validate the pipeline and to validate the software product in some sense. You would still hope to validate the, if you're unsure how accurate it is, then with a quantum computer, you would have still an accuracy guarantee, right? So you could put on top of it, you would get accuracy guarantees. It could also be that, of course, that it'd be faster, for instance. But yeah, it's different.
Someone else with a question? I have a silly one also while you. Oh, go ahead.
But I read the Schrodinger's book. What is life?
Yeah, I also
really
read it.
interesting because it links the origin of life with entropy and
Yes.
things like that. And with today's understanding of how quantum mechanics could play a role into the building of the first cell, I wonder if this kind of stuff cannot be used to simulate, I mean, the first proto cells or something like that. I mean, piece of them, maybe, of course, because I know that they have a lot of problems to simulate that in real.
Oh yeah, okay,
labs.
it's a
They
very
cannot
interesting
do
idea.
it.
Yeah, I hadn't thought
They
about it.
extremely complicated things, and that doesn't work most of the time. And,
Yeah, maybe. Yeah, that's very interesting point. Yeah, good point. Actually, there's this one small point I would like to that I forgot to mention is that this when you think about quantum hardware, this project put the spotlight on one particular aspect of quantum hardware, and that is speed. So we've talked a lot within the project about how many training data points the quantum computer needs to produce, and my colleagues they say 4,000. Okay, so they think that we need at least 4,000 data points coming from the quantum computer, and some of these platforms are really slow. So if you multiply slow by 4,000, it's very slow. So it might actually be that in the future, because I personally had this, I was kind of like, hey, let's build a quantum computer, right? So I actually don't care how fast it is. Let's just build it. But now when you see a project like this, and then you see that a single energy computation would take an hour, right? And you multiply an hour by 4,000, I don't know what comes out, but it's quite a lot, right? It's like the order of months, I think. Right, so you really put the spotlight on the speed of the platforms, and therefore this discussion. So atomic platforms are rather slow. These hardware platforms, like this year's Nobel Prize precursor or like follow-ups, are faster. So it puts a little bit the spotlight on this discussion, and maybe I think this is one thing to keep in mind when we talk about it in the future.
It might be that for some molecules, the Hamiltonian is hard, right?
That what?
That the Hamiltonian is hard to simulate, hard in the complexity theory hard sense. As in, we don't know whether the quantum computer will actually be able to do it in any reasonable amount of time.
Yeah, but the Hamiltonians, sure. I mean, you might not be able to produce a good starting state, right? You might, for instance, produce not a good starting state. We believe that for these biological problems, a good starting state should be possible. Then the problem is like how complicated is the Hamiltonian? That it's more the question how long it takes. It comes again to this time thing. So I think the system in itself is not so big, but if you have to do a 10 to the 12 gates or something, it's a lot. Yeah.
But empirically, people believe that these sort of systems, they are easy, whatever that means.
They're easy.
Easy as in they're not complexity theoretically hard. They're just.
I think there was some kind of I don't know who believes. I mean, I think this is maybe also something in this chemistry in this biological chemistry realm, right? These are single instances. So it's like, this is a single instance problem. It's very hard to now say, what does complexity theory say about it, right? So you would need to have like sequences of problems, and you can look at like changing the basis set and how does complexity evolve. But I think it's very hard to say something concrete good there, at least for me at the moment.
I have just one more question. So first of all, I think it's thanks for the talk. I really like that fact that you've made like a full stack structure where you integrate the quantum computer exactly where it needs to be. I think that's something that we should all be thinking more about. And then, so I'm curious to think what you think. So you mentioned like what you think is important on the experimental side, but on the theory side, what do you think is the like bottleneck there? So like one idea that immediately comes to mind is the fact that your Hamiltonians seem to be, you said they're like random matrices. So that's kind of some of the state-of-the-art methods like LCU, they require usually some assumptions on the Hamiltonian. Like there are all these papers about Hamiltonians. I can't even remember the names of these different assumptions. Like, well, they're sparse, and then there are some low interaction, and then there was another one I don't remember what it's called. And that, but like, is there some specific type of structure that you could see in your types of Hamiltonians that we should be working on, or should we be working to make Hamiltonian simulation algorithms for absolutely random matrices, or is there something else as well that you think?
Yeah, I don't know. I think so personally, I think my contribution, or I think maybe part of the contribution of this project, lies not either in the chemistry nor in the algorithms, but lies in the interaction. I think a lot of the discussion on using quantum computing for chemistry is based on the fact that you had whatever 60 years of quantum chemistry, or 80 years, I don't know how many years of quantum chemistry, and then now everything is like high power developed, and now you're trying to improve on that. But I think this might not be the right thing. You might have to kind of like go back, right, to go back to the beginning, and not make these 5,000 steps that were adjusted to having a classical computer in your lab. And you might need to kind of rethink the whole thing. So you need to kind of like, and I think, yeah, you need to rethink it together with the chemists. I'm not sure if that answers your question, but in some sense, I think that could lead to fundamentally new ideas of where to start and where to end. I think quantum computing, I guess, most naturally comes out of the more physicsy type community, and I think at least that is where we hope to make some contribution here with this project in the interaction, and that might lead to improvements. Yeah.
I'll allow myself a last question. Where are you heading next with this project?
It's a good question. It's a very good question. Now we're continuing the I mean, of course, also in the direction of using quantum computers to do it, right? Like slotting a quantum computer in. That's one part. Personally, I would like to have more smaller trial systems and model systems on which to apply this, right? So like more the physics approach. I would kind of like go a little bit like to go halfway to physics. You can look at other systems. It doesn't have to be docking problems. It can be other problems. Other problems from biology, other methods. So it's like, imagine this is like one thing, and like each module can be kind of like swapped against other modules for better situations and improved situations. And I think, so it's become more like a blueprint that I hope people can build on. And it's like open source. If you want to help us build on it, just get in touch.
Thank you very much. So